This is the demonstration video for the WIMPAVR with added instructions increment and decrement. First, we will go through the expected operations of increment and decrement. Increment is a one-word instruction that takes one clock cycle to complete. The expected operation is that 1 is added to register RD and the new value is stored back into register RD. It increments the program counter and the C flag is not affected by the increment instruction. Similarly, decrement is also a one-word instruction that takes one clock cycle to complete. The expected operation is that 1 is subtracted from register RD and the new value is stored back into register RD. The program counter increments and the C flag is once again not affected by the decrement instruction. Now we will take a look at the test program that will be used to test the system. First, we start at memory address 00. This address contains a load instruction where FF is loaded into register 31. This tests the operation of the load instruction. Next, we test the operation of the increment instruction by incrementing R31. Incrementing R31 should cause FF to roll over from FF to 00. In this case, the carry bit should not be high because the increment instruction does not affect the carry bit. Next, we will decrement R31. This will show, once again, that it rolls over, but this time from 00 to FF. After this, we do another load instruction to load the value 01 into register R29. After loading register R29 with 01, we test the move instruction. We move the value from R29 to R30. Now register R30 and R29 should both contain 01. After this, move on to memory address 05. This contains an add instruction. R31 and R30 get added together. This time, the carry bit should go high, and once again, the value in R31 should go from FF to 00. After this, the carry bit is cleared, and then more interesting test cases are loaded into registers R30 and R31. R31 is loaded with AA, and R30 is loaded with 55. These values will be used to test the logical operations. We'll start by testing the AND operation. We'll AND R31 and R30. ANDing AA and 55 should cause the value in R31 to go back to 00. Now with R31 being 00 and R30 still being 55, we test the OR operation. ORing A with 0 should yield a value of A. So in this case, ORing R31, which is 0, with R30, should store the value that was in R30 back into R31. So both registers should contain 55 after the operation completes. With both registers being 55, we test the XOR instruction. XORing anything by itself should yield the value 00. So after this instruction, we should see that R31 becomes 00. After this, we do two more increment instructions. We increment from 00 to 01, and from 01 to 02. Test the decrement instruction again to decrement from 02 back to 01, and the swap instruction is tested. Swapping will switch the nibbles in R31, so now instead of being 01, it'll be 10. After this, we go into a time delay loop. We'll start in the loop by decrementing R31. So we should decrement from 10 to 0F. After decrementing, we go into no op instruction, which increases the time delay. After the no op instruction, we go into our conditional branching. This conditional branching will send us out of the loop if the value in R31 becomes 00. Otherwise, we'll continue on to the instruction in memory address 13, which is a relative jump instruction, which will send us back to the loop flag, and we will continue to decrement. After R31 becomes 00 and we get out of the loop, we move on to the instruction in memory address 14. This is a set carry instruction. The set carry instruction will indicate that we exited the loop and also show the operation of the set carry instruction. After this, we do more test cases with increment and decrement to show that the increment and decrement operations work with the lower registers as well. We increment R15, So we should see that R15 gets loaded with the value of 1, and then we decrement R0. The initial value of R0 should have been 0, 0. So once again, we should see that it goes from 0, 0 to FF. And then we do another decrement instruction with R0. We should see that it goes from FF to FE. And then finally, we send the processor into an infinite loop. Now we can watch the operation of the processor on the Altera board. Right now, the Altera board is in its initial state, and we need to turn the processor on by flipping switch 17 high. This is indicated by the LED G8 in the middle going high. Right now, I'm in the manual clock mode by having switch 16 and switch 15 at 0. Pressing key 0 will send us into the build state, which is indicated by LED G0 turning on. Flipping switch 14 high will show us the first instruction that is about to be loaded, which is EFFF. This is, once again, the load instruction where we load register R31 with FF. Pressing key 0 again will cause the program counter to point to the memory address 01, and we can see that the instruction EFFF was loaded in. We can watch the value of FF go into register R31 by switching switch 13 high. We see that FF is about to be loaded in, and we can see the current value of R31 by making switches 4 through 0 high. After pressing key 0 again, we should see that FF is loaded into register R31. So now we're on instruction 95FA, because I accidentally skipped instruction 95F3. I pressed it twice, which incremented the register R31 from FF, and so we can see that it wrapped around to 0, 0. So now I'm about to decrement, and we'll go back to FF. Now I'm on the E0D1 instruction. E0D1 loads register R29 with the value 0, 1. So you can flip these switches to look at the current value of register 29. And we should watch that 0, 1 gets loaded into register 29. So now we're on the move instruction. We should see that the value of R30 also becomes 1 because we are doing the move instruction and moving the value of R29 into R30 as well. Current value of R30 is 0. After pressing this, it should become 1. Now we're on the add instruction. Here we're adding registers R31 and R30. The add instruction should cause us, once again, to go for the value of register R31 to go from FF to 0, 0. However, this time, the carry bit is high and the Z bit is high as well. This shows that the value in the register is 0, but also there is a carry out. The add instruction does affect the carry out, while the increment instruction does not. Now we're on the 9488 instruction, which is the clear carry. So we should see that LED R1 turns off. EAFA is the instruction that loads R31 with AA. So we see AA about to be loaded in. If we flip back to look at the current value of R31, we see that it's 0, 0 still, which is also indicated by LED R0. The next instruction loads 55 into register R30. Now we carry out the AND instruction. ANDing registers R31 and registers R30 should cause the value 0, 0 to be restored in register R30. The next instruction is the OR instruction. We should see that ORing 0, 0 and 55 should store 55 in register R31, sorry. The next instruction is the XOR instruction. XORing R31 and R30 should store the value 0, 0 in R31. The next instruction is an increment instruction. R31 is currently at 0, 0, and we increment to 0, 1. We can see that the Z bit just turned off. We increment again to 0, 2, and then we do our decrement instruction to go back to 0, 1. 95F2 is our swap instruction, so we should see that instead of having 0, 1 in R31, we should now have 1, 0 after the instruction executes. Now we enter the time delay loop. We start the time delay loop with our decrement instruction, which is 95FA. Decrementing R31 from 1, 0 should make the value 0F. Now we have our no-op instruction to increase our time delay. There's our conditional branching. The value of R31 is not 0, so we will continue to loop until it is. CFFC is our relative jump, which sends us back to the loop flag, which will cause us to continue to decrement. So now I'm just going to start pressing the button, and we can watch the decrementation of R31. Now that we're at a value of 0, 1 in R31, and we're about to load the value 0, 0 back in, we should see that after we reach the branch instruction again, the BRBSZ, the conditional branching, that we should jump out and no longer loop. After we get out of the loop, we should see that our next instruction to execute is 9408, which is our set carry. Our set carry, which is indicated by LED R1, will become high and indicate that our set carry operation is working and also that we've exited the loop. Now we're loading we're still in, that was our decrement, and now we just loaded 0, 0 into R31. We're still in the loop. So now that it's 0, 0, we should see that we get out, and here's our branch instruction, and we'll see that we no longer loop. CFFC, we passed over. 9408 is our set carry, so after this instruction is executed, we should see LED R1 turn on. 94F3 is our next instruction, which is our increment for register 15. Let's look at the value of register 15 by flipping the switch 4 low. Right now it's 0, 0. After pressing the key 0, we should see that 0, 1 is loaded. It is. The next instruction is 940A. This is a decrement instruction for R0. We can look at the current value of R0 by flipping switches 4 through 0 low. The current value is 0, 0, and after key 0 is pressed, FF will be loaded. Doing it one more time, we'll load register R0 with FE, and now we are at CFFF. This is our infinite loop. We can reset the processor to start over by flipping switch 17 low and pressing key 0.